two numbers. That is all it takes to break the universe. Not a collision of galaxies, not the death of a star, not some violent rupture in the fabric of space-time. Just two numbers, measured with extraordinary care by two separate teams of scientists using two entirely different methods, arriving at two answers that refuse to agree. And tonight, on the Science Pillow, we are going to find out why those two numbers have shaken the foundations of everything we thought we knew about the cosmos. Settle in. Let the room go quiet. Let the hum of the day dissolve into the gentle dark behind your eyelids. There are no advertisements in this video. There is only the vast, patient sky, and a mystery that no one on Earth has been able to solve. We are going to take a long, unhurried journey through the deepest question in modern cosmology. We will start at the beginning, not the beginning of the universe, but the beginning of the idea that the universe might be moving. That it might not be the fixed, eternal backdrop our ancestors imagined, but something restless, something alive, something that has been stretching itself apart since the first fraction of the first second of its existence, and has never stopped. This is the story of the Hubble Tension. It is the story of how two impeccably precise measurements of the same fundamental property of the universe, its rate of expansion, came to disagree so profoundly that physicists are now forced to consider the possibility that our best model of the cosmos is incomplete. That somewhere in the elegant equations that have guided our understanding of reality for decades, something is missing, something fundamental, something that, when finally understood, may change the way we think about space, time, matter, and energy. But before we get to the tension, we need to understand the expansion. And before we understand the expansion, we need to go back to a time when the very idea that the universe could be expanding would have seemed absurd. For most of human history, the universe was considered static, unchanging. The stars moved across the sky in predictable arcs, the planets wandered their familiar paths, and the great dome of the heavens remained, to all appearances, exactly as it had always been. The ancient Greeks imagined celestial spheres of crystal, rotating in perfect harmony. Medieval scholars saw the cosmos as a fixed hierarchy, Earth at the center, the stars embedded in an outermost shell like diamonds, pressed into dark glass. Even Isaac Newton, whose laws of motion and gravity transformed our understanding of the physical world, struggled with the implications of his own equations. If every object with mass attracts every other object with mass, then why hadn't all the matter in the universe collapsed into a single point? Newton's uncomfortable answer was that the universe must be infinite and roughly uniform. Every star pulled equally in all directions, resulting in a precarious balance, a cosmic stalemate. It was a deeply unsatisfying solution, and it was wrong. The first real crack in this ancient assumption came not from a telescope pointed at the sky, but from a set of equations written on paper. In 1922, a Russian physicist and mathematician named Alexander Friedmann was working through the implications of Albert Einstein's general theory of relativity. The revolutionary framework that described gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy, Einstein showed, bend the geometry of the universe. Planets orbit stars not because they are pulled by invisible strings, but because they follow the curved paths that massive objects create in the fabric of space and time. Friedmann took Einstein's field equations and applied them to the universe as a whole. What he found was startling. The equations did not permit a static universe. They demanded motion. The universe, according to the mathematics, had to be either expanding or contracting. It could not simply sit still. Einstein himself was troubled by this result. So troubled, in fact, that he had already introduced an extra term into his equations, a cosmological constant, a kind of mathematical pressure valve designed to hold the universe in place. He called it lambda. Its sole purpose was to counteract gravity on cosmic scales, to keep the stars from falling inward, to preserve the stillness that seemed so obviously true. When Friedmann's work suggested that this stillness was an illusion, Einstein dismissed it as a mathematical curiosity. The universe, he insisted, was not expanding. He would later call that insistence the greatest blunder of his career. Though even that famous remark may be apocryphal, we are not entirely sure Einstein ever used those exact words. What we do know is that the cosmological constant would return decades later in a form that Einstein could never have anticipated. But that is a story for later. Friedmann was not alone in his mathematical foresight. A few years after his initial work, a Belgian priest and physicist named Georges Lemaitre independently derived the same expanding universe solutions from Einstein's equations. Lemaitre went further than Friedmann, however. He connected the mathematics to observations that were already available, measurements of the redshifts of distant nebulae made by the American astronomer Vesto Slipher at the Lowell Observatory in Arizona. Slipher had been systematically measuring the spectra of spiral nebulae since 1912, and he had found something puzzling. The vast majority of them showed red-shifted spectra, meaning they were moving away from us. A few were blue-shifted, approaching, but the overall trend was unmistakable. The universe appeared to be dispersing. Lemaitre, working at the Catholic University of Louvain, combined Slipher's redshift data with his own theoretical framework and, in 1927, published a paper in a relatively obscure Belgian journal proposing that the universe is expanding and estimating the rate of expansion. His paper preceded Hubble's famous work by 2 years, but it was written in French, published in a journal that few astronomers outside Belgium read, and its significance was not widely recognized at the time. History is not always fair in how it assigns credit. The expansion of the universe is named after Hubble, not Lemaitre, in part because of language barriers, in part because of the prestige of American observatories, and in part because Hubble had something that Lemaitre lacked: direct, compelling observational evidence that clinched the case beyond reasonable doubt. In 2018, the International Astronomical Union voted to rename Hubble's law as the Hubble-Lemaitre law, a belated acknowledgement of the Belgian priest's foundational contributions. But Lemaitre's contributions did not end with the expansion. In 1931, he took the idea to its logical conclusion. If the universe is expanding now, he reasoned, then it must have been smaller in the past. And if you trace the expansion backward far enough, you arrive at a state of extreme compression, what Lemaitre poetically called the primeval atom, a single quantum of energy from which the entire universe sprang forth. This was the first articulation of what we now call the Big Bang theory, and it came from a Catholic priest who saw no contradiction between his faith and his physics. The universe had a beginning. It was born, and its birth could be studied with the tools of science. Not everyone was convinced. The British astronomer Fred Hoyle, a fierce opponent of the idea, derisively called it the Big Bang during a BBC radio broadcast in 1949, intending the name as mockery. The name stuck. Science has a sense of humor. But before Lemaitre's primeval atom, before the Big Bang theory, before the cosmic, microwave background confirmed it all, there was Hubble. And Hubble's contribution was not primarily theoretical. It was observational. It was the patient, meticulous work of pointing a telescope at the sky, night after night, recording the light from distant objects, and letting the data speak. The man who proved it was working at the Mount Wilson Observatory in the mountains above Los Angeles, peering through what was then the largest telescope in the world. The 100-inch Hooker telescope, with its massive mirror ground from a single disk of glass shipped from France, was the technological marvel of its age. It gathered light with an efficiency that no previous instrument had matched, revealing details in distant nebulae that had never been seen before. His name was Edwin Hubble. In 1929, Hubble published a paper that would change the course of human thought. He had been studying the light from distant galaxies, though at the time many astronomers still referred to them as nebulae, uncertain whether they were clouds of gas within our own Milky Way or independent island universes far beyond it. Hubble had already helped settle that debate a few years earlier, using a class of pulsating stars called Cepheid variables to demonstrate that the Andromeda Nebula was far too distant to be part of our galaxy. It was a galaxy in its own right, separated from us by a gulf of empty space so vast that light itself needed more than 2 million years to cross it. But now Hubble was after something even more profound. He was looking at the light from these distant galaxies and noticing something peculiar. The light was shifted. Specifically, the spectral lines, the characteristic fingerprints of chemical elements that appear as bright or dark bands when light is split into its component wavelengths, were displaced toward the red end of the spectrum. This phenomenon, known as redshift, had been observed before. It was well understood as a consequence of the Doppler effect, the same principle that causes the pitch of an ambulance siren to drop as it moves away from you. When a source of light moves away from an observer, the wavelengths of that light are stretched, shifting them toward the red. When it moves toward the observer, the wavelengths are compressed, shifting them toward the blue. What Hubble discovered was that nearly every galaxy he observed was redshifted. They were all moving away from us, and not randomly. There was a pattern, a beautiful, elegant, unmistakable pattern. The farther away a galaxy was, the faster it was receding. This relationship, velocity proportional to distance, was stunningly simple. Hubble plotted the recession velocities of galaxies against their estimated distances, and the data points fell along a straight line. The slope of that line represented a constant, a single number that described how quickly the universe was expanding at any given distance. It became known as the Hubble constant, denoted by the symbol h0. The implications were staggering. If every galaxy is moving away from every other galaxy, and the speed of recession increases with distance, then the universe is not static. It is swelling. Space itself is stretching, carrying the galaxies along with it like raisins in a loaf of bread that is rising in an oven. The galaxies are not moving through space away from some central point of explosion. Rather, the space between them is expanding. Every point in the universe is moving away from every other point. There is no center. There is no edge. There is only expansion, happening everywhere, all at once, in every direction. Imagine standing on the surface of a balloon that is being inflated. You draw several dots on the balloon with a marker. As the balloon expands, every dot moves away from every other dot. No single dot is at the center of the expansion. The expansion is a property of the surface itself. Now imagine that the surface is not two-dimensional but three-dimensional, or rather four-dimensional if you include time. That is the universe. That is what Hubble's observations revealed. This is a concept that defeats intuition. We are accustomed to thinking of expansion as something that happens within space. A gas cloud expanding into the vacuum around it. A shock wave propagating outward from an explosion. The ripples spreading across a pond from the point where a stone was dropped. In all of these cases, there is a center, a point of origin, and an edge, a boundary beyond which the expansion has not yet reached. The expansion of the universe has neither. When cosmologists say the universe is expanding, they do not mean that the galaxies are flying outward through a pre-existing space, like shrapnel from a bomb. They mean that space itself is stretching. New space is being created between the galaxies, not at the edges of some cosmic boundary, but everywhere, uniformly, all at once. The galaxies are not moving through space. They are being carried along by space as it expands. It is not the galaxies that are in motion. It is the fabric of reality itself. This distinction matters profoundly. If the galaxies were flying through space, there would be a center, the point from which they were all receding, and there would be an edge, the farthest point the expansion has reached. But if space itself is expanding, there is no center and no edge. Every point in the universe is equivalent. Every observer, no matter where they are, sees the same pattern. All distant galaxies receding, with the speed of recession proportional to the distance. The view from the Milky Way is no different from the view from a galaxy in the Virgo cluster, or a galaxy at the edge of the observable universe. Everyone sees themselves at the center of the expansion, and no one is. This is a humbling realization. It strips away the last vestiges of cosmic specialness. Copernicus showed that the Earth is not at the center of the solar system. Galileo showed that the Sun is not at the center of the universe. Harlow Shapley showed that the Sun is not at the center of the Milky Way. And Hubble showed that the Milky Way is not at the center of the expansion. There is no center. The universe does not have a middle. It has only an everywhere. And if the universe is expanding now, then it must have been smaller in the past. Run the clock backward, and the galaxies draw closer together. The space between them shrinks. The temperature rises. The density increases. Go far enough back, and everything, all the matter, all the energy, all of space and time, converges to a single point of unimaginable density and temperature. A singularity, a beginning, the Big Bang. Hubble's discovery did not just reveal that the universe is expanding. It revealed that the universe has a history. It was born, it has aged, and its future, whether it will expand forever, slow down and stop, or eventually collapse back in on itself, depends on the precise value of the number that Hubble first estimated from his plots of galaxy velocities and distances. The Hubble constant, h0. That number, it turns out, is extraordinarily difficult to pin down. Hubble's original estimate, published in 1929, was approximately 500 kilometers per second per megaparsec. A megaparsec is a unit of distance used in astronomy, equivalent to about 3.26 million light-years. So Hubble was saying that for every megaparsec of distance between us and a galaxy, that galaxy appears to be receding at an additional 500 kilometers per second. That estimate was wildly off. We know now that the true value is somewhere in the neighborhood of 70, not 500. The error was enormous, and it stemmed largely from inaccuracies in the distance measurements available at the time. Measuring cosmic distances is one of the hardest problems in all of astronomy. The universe does not come with a ruler. Stars do not carry labels announcing how far away they are. Every distance estimate relies on a chain of assumptions and calibrations, each building on the one before, each introducing its own potential for error. But the principle Hubble established was correct. The universe is expanding, and the rate of that expansion can be described by a single number. Get that number right, and you unlock the age of the universe, its size, its geometry, its ultimate fate. Get it wrong, and you get lost. For nearly a century, astronomers have been trying to measure H0 with ever-increasing precision. They have built bigger telescopes, launched satellites, developed new techniques, and pushed the boundaries of observational science to their absolute limits. And for most of that century, the quest to measure the Hubble constant was a story of steady progress, of uncertainties shrinking, of estimates converging, of confidence growing that we were closing in on the true value. Until, quite recently, something went wrong. Two teams, using two completely different approaches, each measured with extraordinary care, arrived at two values of the Hubble constant that do not agree. The difference is not large in absolute terms, roughly 6 kilometers per second per megaparsec. But relative to the precision of the measurements, the disagreement is enormous. It is like two master clockmakers, each building the most accurate timepiece ever constructed, and discovering that their clocks disagree by a full second every hour. The clocks are too good for the discrepancy to be a mistake. Something deeper is going on. This disagreement is called the Hubble Tension, and it has become, in the words of some physicists, the most important unsolved problem in cosmology. Let us drift now into the methods. Let us follow the astronomers who climbed the rungs of an invisible ladder stretching from our own solar system to the farthest reaches of the observable universe, and let us see what they found when they reached the top. Part 2. The Cosmic Distance Ladder. The universe does not reveal its distances willingly. Stand on a hilltop on a clear night and look up. Every star you see appears as a point of light, sharp and dimensionless, offering no obvious clue about whether it is relatively close, a few light years away, or impossibly far, a traveler whose light has been journeying for millennia. The brightest star in the sky, Sirius, is a mere 8.6 light-years from Earth. The faintest stars visible to the naked eye may be hundreds or thousands of light-years distant. Yet, to your unaided eye, they all look more or less the same. Tiny, twinkling, anonymous. This fundamental ambiguity, the inability to distinguish between a dim star that is close and a bright star that is far, has plagued astronomers for centuries. And overcoming it has required one of the most ingenious and painstaking constructions in all of science. It is called the Cosmic Distance Ladder. And each rung of this ladder is a different technique for measuring distance, each one reaching farther into the cosmos than the last, each one calibrated against the rung below it. The lowest rung is the most direct. It is called parallax, and it is based on a principle so simple that you can demonstrate it with your own hand. Hold your thumb at arm's length and close one eye. Note the position of your thumb against the background. Now close that eye and open the other. Your thumb appears to jump. The apparent shift in position, caused by the slight difference in viewing angle between your two eyes, is parallax. The closer your thumb is to your face, the greater the jump. The farther away it is, the smaller the shift. Astronomers use the same principle, but on a vastly larger scale. Instead of two eyes separated by a few centimeters, they use the Earth itself as a baseline, taking observations of a nearby star 6 months apart, when the Earth is on opposite sides of its orbit around the Sun. The diameter of Earth's orbit, roughly 300 million kilometers, serves as the distance between the two eyes. By measuring the tiny apparent shift of a star against the background of much more distant stars, astronomers can calculate its distance using simple trigonometry. This technique works beautifully for stars within a few hundred light years. The European Space Agency's Hipparcos satellite, launched in 1989, measured the parallaxes of over 100,000 stars with unprecedented accuracy. Its successor, the Gaia spacecraft, launched in 2013, has extended this precision dramatically, cataloging the positions and distances of nearly 2 billion stars in our galaxy. Gaia's measurements are so precise that it can detect the parallax shift of a star thousands of light years away. A shift so small that it would be like trying to measure the width of a human hair from a distance of several hundred kilometers. To appreciate how remarkable this is, consider the numbers. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. Its parallax, the apparent shift in position as the Earth orbits the Sun, is roughly 0.76 arc-seconds. An arc-second is 1/3600th of a degree. It is a tiny angle. Now consider a star 1,000 light-years away. Its parallax is roughly 1,000 times smaller, less than 1,000th of an arc-second. Measuring such infinitesimal angles requires instruments of extraordinary sensitivity, and even the slightest systematic error, a tiny distortion in the optics, a subtle thermal expansion of the spacecraft, an imperfect model of the detector's response, can corrupt the measurement. Gaia's engineering team solved these problems with heroic attention to detail. The spacecraft rotates slowly, scanning the sky in great circles, building up a self-consistent map of stellar positions from billions of individual measurements. The data processing alone is a computational tour de force, involving the simultaneous solution of billions of equations to extract the positions, distances, and motions of nearly 2 billion individual stars. It is one of the largest data analysis problems ever attempted in astronomy. But even Gaia has its limits. The parallax method can only reach so far. Beyond a certain distance, the apparent shift becomes too small to measure, even with the most sensitive instruments. To go further, astronomers need a different approach. This is where the second rung of the ladder comes in, and it was built, in large part, by a woman whose contributions were overlooked for decades. Her name was Henrietta Leavitt. She worked at the Harvard College Observatory in the early 1900s, at a time when women were employed as computers, human calculators tasked with the tedious work of examining photographic plates and cataloging the brightness of stars. Leavitt was assigned to study a class of stars called Cepheid variables, stars whose brightness fluctuates in a regular rhythmic pattern, brightening and dimming over periods ranging from a few days to several weeks. The physics behind this pulsation is beautiful. Cepheid variables are massive, evolved stars, typically 5 to 20 times the mass of our Sun, that have entered an unstable phase of their lives. Their outer layers oscillate, expanding and contracting in a regular rhythm, driven by a mechanism involving the ionization of helium in the star's atmosphere. When the star contracts, its outer layers compress and heat up, ionizing the helium atoms. Ionized helium is more opaque to radiation, so it traps energy, building up pressure. This pressure causes the outer layers to expand, cooling them and allowing the helium to recombine and become transparent again. The pressure drops, the layers fall inward, the cycle repeats. It is, in essence, a cosmic heartbeat. A star breathing in and out with a regularity as dependable as a metronome. Leavitt was examining Cepheids in the small Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere. Because all the stars in this galaxy are roughly the same distance from Earth, any differences in their apparent brightness must reflect genuine differences in their intrinsic luminosity. And Leavitt noticed something remarkable. The brighter Cepheids pulsated more slowly. The dimmer ones pulsated more quickly. There was a precise, predictable relationship between a Cepheid's period of pulsation and its true brightness. She published her findings in 1912, in a brief paper that was characteristically modest. The Harvard Observatory Circular Number 173 contained just a few pages of data and a single world-changing graph. Leavitt did not speculate on the implications. She simply presented the facts. But the implications were enormous, and they were recognized almost immediately by other astronomers. This was a revelation. Because if you can determine a star's true brightness, its luminosity, then you can compare it to its apparent brightness as seen from Earth, and calculate how far away it must be. A candle that appears dim might be a small candle nearby or a bonfire far away. But if you know it is a bonfire, you can work out the distance from its apparent dimness. Cepheid variables, thanks to Leavitt's discovery, became standard candles, objects of known luminosity that could serve as cosmic mile markers. The Swedish mathematician Gösta Mittag-Leffler reportedly considered nominating Leavitt for the Nobel Prize in Physics, but he wrote to her in 1921, only to learn that she had died of cancer 4 years earlier, at the age of 53. The Nobel Prize is not awarded posthumously. Leavitt's contribution, one of the most consequential discoveries in the history of astronomy, went unrecognized by the world's most prestigious scientific award. This is the tool that Edwin Hubble used to measure the distance to the Andromeda Galaxy. He identified Cepheid variables in Andromeda, measured their periods, used Leavitt's period luminosity relation to determine their true brightness, and compared that to their apparent brightness. The result? Andromeda was roughly 900,000 light-years away, far beyond the boundaries of our own galaxy. The universe was suddenly much, much bigger than anyone had imagined. Cepheids remain one of the most important distance indicators in astronomy. The Hubble Space Telescope, named fittingly after Edwin Hubble himself, spent years observing Cepheid variables in dozens of galaxies, refining the period luminosity relation, tightening the calibrations, pushing the reach of this technique to distances of about 100 million light-years. A dedicated project called the SH0ES program, led by the Nobel laureate Adam Rees at Johns Hopkins University, has made measuring Cepheid distances its primary mission for more than 2 decades. But Cepheids have a limitation. They are individual stars, and individual stars become impossible to resolve at truly cosmological distances. The farthest galaxies in Hubble's reach are already at the edge of what Cepheids can provide. To go further, you need something brighter, something so luminous that it can be seen across billions of light years. You need a supernova. Not just any supernova. A very specific type called a Type 1a supernova. These explosions occur in binary star systems, where a dense stellar remnant known as a white dwarf, the collapsed core of a dead star roughly the size of Earth but with the mass of our Sun, is slowly siphoning matter from a companion star. As the white dwarf accumulates this stolen material, its mass increases. And there is a critical threshold, the Chandrasekhar limit, named after the Indian-American physicist Subramanian Chandrasekhar, at approximately 1.4 times the mass of the Sun, beyond which the white dwarf can no longer support itself against gravitational collapse. When a white dwarf reaches this limit, it does not collapse into a neutron star or a black hole, as more massive stars do. Instead, the carbon and oxygen in its core ignite in a thermonuclear detonation, a runaway fusion reaction that consumes the entire star in a matter of seconds, releasing an amount of energy so prodigious that for a few weeks this single exploding star can outshine its entire host galaxy. Billions upon billions of stars, outshone by one. The beauty of Type 1. A supernovae, from the perspective of distance measurement, is their remarkable uniformity. Because they all explode at approximately the same mass, the Chandrasekhar limit, they all release approximately the same amount of energy. Their peak luminosity is nearly identical from one event to the next. This makes them extraordinarily reliable standard candles. If you observe a Type 1a supernova in a distant galaxy, you know how bright it truly is. You measure how bright it appears. The difference tells you the distance. In practice, the situation is slightly more complicated. Not all Type 1a supernovae are exactly alike. Some are a little brighter, some a little dimmer, and these variations correlate with other properties of the explosion. The speed at which the brightness declines after peak, the color of the supernova at maximum light, the properties of the host galaxy. Astronomers have developed sophisticated methods to account for these variations, standardizing the supernova brightness with corrections that reduce the scatter to a level of about 5 to 7%. This might not sound impressive, but in the context of the vast distances being measured, billions of light years, a 5% uncertainty in distance corresponds to a remarkably precise determination of the expansion rate. It was Type 1a supernovae that delivered one of the most shocking discoveries in the history of science. In 1998, two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using Type 1a supernovae to measure the deceleration of the universe's expansion. The expectation, based on decades of theoretical work, was that the gravitational attraction of all the matter in the universe would be gradually slowing the expansion down, like a ball thrown upward against the pull of gravity. The supernova data would reveal the rate of deceleration, telling us whether the universe would eventually stop expanding and collapse, or continue expanding forever, but at an ever-decreasing rate. What the data showed was the opposite. The distant supernovae were dimmer than expected, farther away than they should have been if the expansion were decelerating. The expansion of the universe was not slowing down. It was speeding up. Something, some mysterious force, some unknown energy, was pushing the galaxies apart with increasing vigor. The universe was accelerating. This discovery, which earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, introduced the concept of dark energy to the world, a form of energy that fills all of space and exerts a negative pressure, driving the accelerated expansion. Dark energy accounts for roughly 68% of the total energy content of the universe, making it the dominant component of the cosmos by a wide margin. And yet, we have almost no idea what it is. It is arguably the deepest mystery in all of physics. The cosmological constant, Einstein's lambda, the very term he had introduced and then regretted, was resurrected as the simplest mathematical description of dark energy. In this picture, empty space itself has a fixed positive energy density, and this energy drives the acceleration. The irony was not lost on the physics community. Einstein's greatest blunder turned out to be, perhaps, his most prescient insight. This technique, the cosmic distance ladder, with its rungs of parallax, Cepheids, and Type 1a supernovae, has allowed astronomers to measure distances to galaxies billions of light-years away. And it was this method, combined with the Cepheid distance ladder below it, that produced one of the two competing values of the Hubble constant. The SH0ES team, led by Adam Rees, uses Cepheid variables to calibrate the distances to nearby galaxies that have also hosted Type 1a supernovae. This calibration anchors the supernova brightness scale. Then, by observing Type 1a supernovae in galaxies much farther away, galaxies receding from us at speeds that are dominated by the expansion of the universe, the team can measure the relationship between distance and recession velocity. The slope of that relationship is the Hubble constant. Their result, refined over many years and many observations, converges on a value of approximately 73 kilometers per second per megaparsec. This number has been tested, cross-checked, and scrutinized by independent teams using different calibration techniques, and it holds firm. The tip of the red giant branch method, which uses the brightest red giant stars as distance indicators instead of Cepheids, produces a similar value. Surface brightness fluctuations, a statistical technique that measures the graininess of the light from distant galaxies, also agrees. The local measurement, the measurement of the expansion rate as determined by observing objects in the relatively nearby universe, points firmly and consistently to a Hubble constant of about 73 kilometers per second per megaparsec. Remember that number. Hold it gently in your mind, because there is another number, and it is different. And the difference, as we shall see, threatens to upend our understanding of the cosmos itself. Let us drift now toward the oldest light in the universe. Let us turn our gaze not outward to the distant galaxies, but backward in time, all the way back to an era when the universe was young, hot, dense, and utterly opaque. Let us listen to the echo of the Big Bang. Part 3. Echoes of the Big Bang. There is a glow that fills the sky. You cannot see it with your eyes. It does not compete with starlight or moonlight. It does not register on photographic film or illuminate the landscape. It is a whisper of radiation so faint, so ancient, so utterly pervasive that for decades no one knew it existed. And when it was finally discovered, it was found entirely by accident. The year was 1964. The place was Holmdel, New Jersey, at a facility belonging to Bell Telephone Laboratories. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna originally built for satellite communications. They were trying to calibrate the antenna for radio astronomy observations, And they had a problem. No matter where they pointed the antenna, north, south, east, west, toward the Milky Way or away from it, they detected a persistent, low-level hiss of microwave radiation. It was everywhere. It was constant. It was annoying. They checked the instrument. They tightened connections. They cooled the receiver. They even cleaned out the pigeon droppings that had accumulated inside the horn. A pair of pigeons had taken up residence, and Penzias and Wilson wondered if the birds' contributions might be the source of the unwanted signal. They were not. The hiss persisted, uniform, isotropic, coming from every direction in the sky with almost exactly the same intensity. Whatever was producing this signal, it was not local, it was not instrumental, it was cosmic. Meanwhile, just 40 miles away at Princeton University, a team of physicists led by Robert Dicke was building their own antenna to search for exactly this kind of radiation. Dicke and his colleagues had predicted that if the Big Bang theory was correct, if the universe had indeed begun in a state of unimaginable heat and density, then the afterglow of that primordial fireball should still be detectable today, cooled by billions of years, of cosmic expansion from a searing inferno to a faint, cold whisper of microwave radiation with a temperature of just a few degrees above absolute zero. When Penzias and Wilson learned of Dicke's prediction, the pieces fell into place. The mysterious hiss was not noise. It was the most ancient light in the universe. It was the cosmic microwave background radiation, the CMB, the thermal echo of the Big Bang itself, released when the universe was roughly 380,000 years old. The discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics. Dicke, whose theoretical prediction had guided the interpretation, did not share the prize, one of the more painful omissions in Nobel history. But the significance of the discovery was beyond dispute. The CMB was the smoking gun for the Big Bang theory. It was the direct physical evidence that the universe had once been unimaginably hot and dense, and that it had been cooling ever since. The rival steady-state theory, which proposed that the universe had always existed in more or less its current form, with new matter continuously created to fill the gaps left by the expansion, could not account for this pervasive background radiation. The Big Bang had won. But the CMB was more than just evidence for the Big Bang. It was a time capsule, a snapshot of the universe as it existed when it was only 380,000 years old, barely a cosmic infant. And embedded in its faint, nearly uniform glow was a wealth of information about the conditions that prevailed in the early universe. Its temperature, its density, its composition, its geometry, and, crucially, the rate at which it was expanding. To understand why the CMB exists, you need to understand what the early universe was like. In the first few 100,000 years after the Big Bang, the universe was so hot and so dense that matter existed as a plasma, a roiling, opaque soup of protons, electrons, and photons, all violently interacting with each other. Photons, particles of light, could not travel in straight lines. Every time a photon was emitted, it immediately collided with a free electron and was scattered in a random direction, like a flashlight beam in thick fog. The universe was blinding, but nothing could be seen. Light was everywhere, but it went nowhere. Then, as the universe expanded, it cooled, and approximately 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin, cool enough for protons and electrons to combine and form neutral hydrogen atoms. This event is called recombination, and it marked one of the most dramatic transitions in cosmic history. With the free electrons now bound into atoms, photons were suddenly free to travel unimpeded. The fog lifted. The universe became transparent. Those photons, the ones released at the moment of recombination, have been traveling through space ever since. For 13.8 billion years, they have been streaming across the cosmos, their wavelengths stretched by the expansion of space from the visible and infrared range into the microwave region of the electromagnetic spectrum. Today, they arrive at our telescopes as a faint, nearly uniform glow, with a temperature of approximately 2.725 degrees above absolute zero. They come from every direction, filling the sky with a gentle thermal hum that carries information about the universe as it was nearly 14 billion years ago. The CMB is not perfectly uniform. If it were, the universe would be featureless. No galaxies, no stars, no planets, no you, no me. Instead, the CMB contains tiny fluctuations, variations in temperature of about 1 part in 100,000. These fluctuations are the fingerprints of quantum fluctuations in the density of matter in the early universe, frozen in place by the rapid expansion of space. Where the density was slightly higher, gravity eventually pulled matter together to form galaxies and clusters of galaxies. Where the density was slightly lower, the voids of the cosmic web emerged. The pattern of fluctuations in the CMB is, in a very real sense, the blueprint of all the large-scale structure in the universe today. Mapping these fluctuations with precision has been one of the great achievements of modern cosmology. The first detailed map was produced by NASA's COBE satellite in the early 1990s, revealing the broad outlines of the CMB's temperature variations. The principal investigator of the COBE experiment, John Mather, shared the 2006 Nobel Prize in Physics for this work, along with George Smoot, who led the analysis of the fluctuations. When Smoot first presented the COBE results at a scientific conference, he showed a map of the sky painted in subtle shades of blue and red. The blue regions slightly cooler, the red regions slightly warmer. The audience gasped. They were looking at the baby picture of the universe. But COBE's resolution was limited. It could see the broad features of the CMB fluctuations, but it could not resolve the fine details, the intricate patterns that encode information about the physics of the early universe. For that, a sharper eye was needed. The physics encoded in the CMB fluctuations is extraordinarily rich. To understand why, we need to consider what was happening in the universe during its first 380,000 years, the era before the CMB was released. The universe at that time was filled with a tightly coupled plasma of baryons, protons and neutrons, electrons and photons, all bound together by electromagnetic interactions. Dark matter was also present, but it did not interact directly with the plasma. It simply provided a gravitational framework, a web of potential wells into which the plasma could fall. Within this plasma, two competing forces were at work. Gravity pulled the plasma toward the centers of dark matter concentrations, compressing it and heating it up. Radiation pressure, the outward push of photons, resisted this compression, pushing the plasma back outward. The result was a series of oscillations, acoustic waves, essentially sound waves, that propagated through the plasma at roughly half the speed of light. These waves were not sound in the everyday sense. There was no air, no medium as we know it. But they were pressure waves, compressions, and rarefactions traveling through the hot plasma like ripples through a pond. These oscillations created a characteristic pattern. Regions that had just reached maximum compression at the moment of recombination, when the universe became transparent and the CMB was released, appear as hot spots in the CMB. Regions that had just reached maximum rarefaction appear as cold spots. And the distance that a sound wave could travel between the Big Bang, recombination, a distance called the sound horizon, defines a characteristic angular scale on the sky. The sound horizon is like a cosmic ruler. Its physical size is determined by well-understood physics, the speed of sound in the plasma, and the age of the universe at recombination. Its apparent angular size in the CMB depends on the geometry of the universe and the distance to the surface of last scattering. By measuring the angular scale of the first acoustic peak, the most prominent feature in the CMB power spectrum, cosmologists can determine the geometry of the universe with remarkable precision. The Planck satellite's measurement confirms that the universe is geometrically flat to within a fraction of a percent, meaning that parallel lines remain parallel forever, and the angles of a triangle sum to exactly 180 degrees, even on cosmic scales. But the power spectrum contains far more than just the first peak. There is a whole series of peaks, each corresponding to a different harmonic of the acoustic oscillations, like the overtones of a musical instrument. The relative heights and positions of these peaks encode information about the ratio of baryons to photons, the density of dark matter, and, critically, the expansion rate of the universe. By fitting a theoretical model to the observed power spectrum, adjusting the parameters until the predicted peaks match the observed peaks, cosmologists can extract the fundamental parameters of the universe with extraordinary precision. This is what the Planck team did. A decade later, the WMAP satellite provided a much sharper picture, pinning down the age of the universe, the proportions of ordinary matter, dark matter, and dark energy, and the overall geometry of space. And in 2013, the European Space Agency's Planck satellite delivered the most precise measurement of the CMB ever made. A map of exquisite detail and breathtaking beauty, showing the faint, modeled pattern of the infant universe with an accuracy that borders on the miraculous. Planck observed the sky in 9 frequency bands, from 30 to 857 gigahertz, allowing it to separate the CMB signal from contaminating foreground emission, dust in our own galaxy, synchrotron radiation from energetic electrons, emission from distant radio sources. The final maps, released after years of painstaking data analysis, represent the cleanest, most detailed portrait of the early universe ever achieved. The Planck data allowed cosmologists to do something remarkable. By analyzing the statistical properties of the CMB fluctuations, their sizes, their amplitudes, their spatial frequencies, they could determine the fundamental parameters of the universe with extraordinary precision. The curvature of space, the density of matter, the proportion of dark energy, and, crucially, the rate at which the universe was expanding when it was 380,000 years old. The picture that emerged from the Planck data is both elegant and deeply strange. The universe, according to Planck, is composed of approximately 68.3% dark energy, 26.8% dark matter, and just 4.9% ordinary matter. The protons, neutrons, and electrons that make up every star, planet, ocean, mountain, and living organism in the cosmos. Everything we can see, everything we have ever touched or measured directly, constitutes less than 5% of the total content of the universe. The rest is invisible. Dark matter does not emit, absorb, or reflect light. Dark energy is not associated with any known particle. Together, they account for 95% of the universe, and we do not know what either of them is. This is the lambda CDM model, named for the cosmological constant, lambda, and cold dark matter, CDM, that dominate its composition. It is the standard model of cosmology, the ICE framework within which nearly all cosmological observations are interpreted. And it works astonishingly well. It correctly predicts the large-scale distribution of galaxies. It accounts for the relative abundances of hydrogen, helium, and lithium produced in the first few minutes after the Big Bang. It explains the observed pattern of fluctuations in the CMB with a precision that is, frankly, breathtaking. The model has just 6 free parameters, 6 numbers that describe the composition, geometry, and initial conditions of the universe. And with these 6 numbers, it can reproduce the observed properties of the cosmos from the first fraction of a second to the present day. It is, by any reasonable standard, one of the most successful scientific models ever devised. And that is precisely what makes the Hubble tension so disturbing. Because the Hubble tension suggests that this model, for all its successes, may be missing something. Now, the expansion rate back then was very different from the expansion rate today. The universe was younger, denser, and expanding much faster. But if you know the expansion rate at that early time, and you know the composition of the universe, how much matter, how much radiation, how much dark energy, then you can use the equations of general relativity to extrapolate forward in time and predict what the expansion rate should be today. It is like watching a ball thrown into the air and calculating, from its initial velocity and the force of gravity, how fast it should be moving when it reaches a particular height. The extrapolation is not a simple calculation. It involves tracking the evolution of the universe through several distinct epochs, each dominated by a different component. In the first few tens of thousands of years, the universe was radiation-dominated. The energy of photons and neutrinos exceeded the energy of matter, and the expansion rate was determined primarily by the radiation density. As the universe expanded and the radiation diluted more rapidly than the matter, the universe transitioned to a matter-dominated era, in which the gravitational pull of dark matter and ordinary matter determined the dynamics. Finally, roughly 5 billion years ago, the energy density of dark energy, which does not dilute as the universe expands, began to exceed the energy density of matter, and the universe entered its current dark energy-dominated era, characterized by accelerated expansion. Each transition changes the rate at which the universe expands. Getting the extrapolation right requires knowing the precise proportions of each component, the time at which each transition occurred, and the equation of state of dark energy. The Planck data, combined with the lambda CDM model, provide all of this information, and the predicted present-day expansion rate is 67.4. The Planck team did this calculation. They took their exquisitely precise measurements of the CMB, fed them into the standard cosmological model, the lambda CDM model, and extrapolated forward to the present day. The result was a Hubble constant of approximately 67.4 kilometers per second per megaparsec. 67.4. Not 73. 67. The difference is about 8%. In everyday life, an 8% discrepancy might seem trivial. If two bathroom scales disagreed by 8% on your weight, you would probably shrug and assume one of them needed recalibrating. But in precision cosmology, where uncertainties have been reduced to the level of 1 or 2%, an 8% difference is not a shrug. It is an alarm. The local measurements, the ones based on the cosmic distance ladder, on Cepheids and supernovae, and the direct observation of galaxies in the nearby universe, say 73. The early universe measurements, the ones based on the CMB, on the physics of the hot plasma that filled space nearly 14 billion years ago, extrapolated forward using the best cosmological model we have, say 67. Both measurements have been scrutinized, challenged, repeated, and refined. Both teams have published their work in the most prestigious scientific journals. Both have been awarded Nobel Prizes for their contributions, and both insist that their result is correct. The tension between these two numbers has been growing for over a decade. With each new measurement, with each improvement in precision, the gap has not closed. It has widened. The statistical significance of the discrepancy now exceeds 5 sigma, a threshold that, in the conventions of particle physics, is considered the gold standard for a genuine discovery. A 5 sigma result means that the probability of the disagreement being due to random chance is less than 1 in 3.5 million. Something is wrong, something fundamental, and nobody knows what it is. Let us rest here for a moment. Feel the weight of that uncertainty. 2 measurements, 2 teams, 2 answers, both right, both incompatible. And let us now look more closely at the tension itself, at the history of its emergence, the attempts to resolve it, and the unsettling possibility that our best model of the universe is not wrong in some small, correctable way, but wrong in a way that requires entirely new physics to explain. Part 4. When the numbers broke. The Hubble tension did not arrive with a dramatic announcement. It crept in slowly, like a shadow lengthening across a sunlit floor. Noticed at first only by the specialists who spent their days calibrating instruments and cross-checking data. For a long time, many cosmologists assumed the discrepancy was temporary, a systematic error lurking somewhere in the data, a calibration issue that would eventually be identified and corrected. Science, after all, is full of apparent anomalies that dissolve under closer inspection. A detector might have an unknown bias. A model might contain an oversimplified assumption. A distance measurement might be subtly corrupted by intervening dust or gravitational lensing. These things happen. They are the routine hazards of empirical science, and they are usually resolved with better data and more careful analysis. But the Hubble tension has not dissolved. It has hardened. The earliest hints appeared in the years following the release of the first WMAP data in 2003. WMAP's measurement of the Hubble constant, derived from the CMB, was in the low 70s, consistent within the uncertainties with the local measurements available at the time. The error bars were large enough to accommodate both values. There was no tension. There was only imprecision. But as the measurements improved, as WMAP collected more data, as the SH0ES team refined its Cepheid calibrations, as the Planck satellite delivered its revolutionary maps of the CMB, the error bars shrank. And as they shrank, the two values did not converge. They drifted apart. By 2014, the discrepancy was sitting at about 3 sigma, statistically significant, but not yet alarming. Many researchers attributed it to some unidentified systematic effect and expected it to resolve with the next round of data. It did not. By 2018, the tension had grown to roughly 4 sigma. Papers were published, expressing concern. Conferences were organized. Working groups were formed. Still, many cosmologists counseled patience. 4 sigma was significant, but it had happened before in the history of physics, and sometimes the anomaly went away. In 2019, the SH0ES team published a landmark paper in the Astrophysical Journal. Using a combination of Hubble Space Telescope observations of Cepheid variables and Type 1a supernovae, they reported a local Hubble constant of 74.03, plus or minus 1.42 kilometers per second per megaparsec. The Planck result, refined with the satellite's final data release, stood at 67.4, plus or minus 0.5. The gap between the two, roughly 6.6 kilometers per second per megaparsec, now exceeded 4.4 sigma. The probability of this being a statistical fluke was less than 1 in 100,000. The reaction in the physics community was a mixture of excitement and unease. Excitement because a genuine discrepancy at this level would imply new physics, something beyond the standard model of cosmology, something previously unknown about the fundamental nature of the universe. And unease because new physics is a double-edged sword. It means that something we believed to be true is not. It means that the lambda CDM model, the framework that has successfully described the large-scale structure, evolution, and composition of the universe for decades, may be incomplete. And if it is incomplete, we do not know what is missing. Since then, the tension has only deepened. In 2020, the Atacama Cosmology Telescope, an independent ground-based CMB experiment in Chile, released its own measurement of the Hubble constant from the CMB. The result confirmed Planck's value, approximately 67.6, and closed the door on the possibility that the discrepancy was an artifact of the Planck satellite's specific instrumentation or data analysis pipeline. The CMB value was not a fluke. It was robust. On the other side, new distance ladder measurements continued to corroborate the higher value. The Carnegie-Chicago Hubble program used the tip of the red giant branch method, an alternative to Cepheids, and found a Hubble constant in the low 70s. Gravitational lensing time delays, measured by the TDCO-SMO collaboration, produced a value of about 71.6, consistent with the local measurements. Surface brightness fluctuations, yet another independent technique, also pointed to the mid-70s. It is worth pausing here to appreciate the sheer effort that goes into these measurements. Each rung of the cosmic distance ladder requires years of telescope time, painstaking data reduction, and careful assessment of systematic uncertainties. The SH0ES team alone has spent more than 2 decades refining its methodology. Adam Rice, who shared the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion of the universe, itself one of the most shocking discoveries in the history of science, has devoted the second act of his career to measuring H0 with ever greater precision. His team has observed Cepheid variables in dozens of galaxies with the Hubble Space Telescope, calibrated their brightness using multiple independent geometric anchors, and cross-checked their supernova distances against every available benchmark. The effort on the CMB side has been equally heroic. The Planck satellite operated for over 4 years, scanning the sky in 9 frequency bands, accumulating billions of individual measurements. The data analysis pipeline involved hundreds of scientists across dozens of institutions, each contributing specialized expertise in calibration, foreground removal, beam characterization, and statistical inference. The final Planck results, published in a series of papers that span thousands of pages, represent one of the most thoroughly validated scientific analyses ever conducted. And yet the two answers disagree. There is a human dimension to this story that should not be overlooked. The Hubble tension is not just a dispute between numbers. It is a dispute between communities. The local distance ladder community and the CMB community, each with its own methods, its own culture, its own standards of evidence, and its own deeply held convictions about what the data are telling us. The early years of the tension were marked by a certain wariness between these groups, a tendency for each side to scrutinize the other's work more critically than its own. Papers were published with titles that hinted at the underlying stakes: A Strong Lens on the Hubble Constant, Planck Evidence for a Closed Universe, The Trouble with H0. But as the tension has grown, so has the dialogue. Joint workshops have been organized, bringing together experts from both sides to compare methods, share data, and identify potential sources of error. The tone has shifted from adversarial to collaborative, driven by a shared recognition that if the tension is real, if it truly reflects new physics, then it belongs to everyone. It is not a problem to be won, but a mystery to be solved. And in early 2026, that collaborative spirit reached a new milestone. An international collaboration of cosmologists took the extraordinary step of combining all the major local measurement techniques into a single unified analysis. The Local Distance Network, as it was called, brought together researchers who had previously published independent and sometimes conflicting results. They developed a common statistical framework, a way of combining measurements from Cepheids, TRGB stars, surface brightness fluctuations, and Miras into a single self-consistent estimate of the Hubble constant. The results, published in Astronomy and Astrophysics, represented the most precise local measurement of the Hubble constant ever achieved, an accuracy of approximately 1%. The unified value confirmed what each individual technique had been saying for years. The Hubble constant, as measured from the nearby universe, is firmly around 73. The lead author, Stefano Casertano of the Space Telescope Science Institute, described the significance with characteristic precision. The prevailing cosmological model predicts that the Hubble constant should be 10% smaller than what is measured directly. The difference is more than 5 times the combined uncertainty of both models and measurements. This is not a discrepancy that can be wished away with better data or more careful analysis. It is a statement about the universe itself. The tension now exceeds 5 sigma, 5 standard deviations. In the language of statistics, this means that if the standard cosmological model is correct, the probability of observing a discrepancy this large by chance alone is less than 1 in 3.5 million. 1 in 3.5 million. Let that settle for a moment. Imagine flipping a coin and getting heads 22 times in a row. That is the kind of improbability we are talking about. Not impossible, strictly speaking, but so unlikely that it strains credulity. At some point, you stop blaming the coin and start questioning the table. So, what could be causing this? Let us consider the possibilities, each one more unsettling than the last. The most conservative explanation is systematic error, a hidden flaw in one or both sets of measurements that mimics a genuine discrepancy. Perhaps the Cepheid distance scale is biased in some subtle way that has not been identified. Perhaps the physics of Type 1a supernovae is more complex than the standard model assumes, introducing variations in their peak luminosity that corrupt the distance measurements. Perhaps the Planck data contain an unrecognized instrumental effect that shifts the inferred value of the Hubble constant. These possibilities have been exhaustively investigated. Multiple teams have independently calibrated the Cepheid distance scale using different methods. Parallax from Gaia, eclipsing binaries in the Large Magellanic Cloud, massers in NGC 4258, and they all agree. The supernova data have been scrutinized for environmental effects, host galaxy properties, and photometric calibration errors. The Planck results have been confirmed by entirely independent CMB experiments, including the Atacama Cosmology Telescope and the South Pole Telescope. None of these investigations have found a systematic error large enough to explain the tension. This does not prove that such an error does not exist. Absence of evidence is not evidence of absence, as the saying goes. But it does make the systematic error explanation increasingly difficult to sustain. The measurements are too independent, too well cross-checked, too carefully controlled. If it is not systematic error, then what? The answer that excites and terrifies physicists in equal measure is new physics. The standard cosmological model, lambda CDM, is built on a set of assumptions about the fundamental constituents of the universe and the laws that govern them. It assumes that gravity is described by general relativity. It assumes that dark energy takes the form of a cosmological constant, Einstein's lambda, whose energy density does not change over time. It assumes that dark matter is cold, meaning it moves slowly compared to light. And it assumes that the universe is homogeneous and isotropic on large scales, that it looks the same in every direction and has the same properties everywhere. If any of these assumptions is wrong, the extrapolation from the early universe to the present day could produce an incorrect prediction for the Hubble constant. The CMB measurement would still be valid. It is a direct observation of the early universe. But the predicted present-day expansion rate, calculated by running the clock forward through the standard model, could be off. And the direction of the discrepancy, the fact that the predicted value is lower than the observed value, provides a crucial clue about what kind of new physics might be at work. The universe, according to the local measurements, is expanding faster than the standard model predicts. Something is making it go faster. Something is giving it an extra push that is not accounted for in our equations. What could that something be? Let us journey now into the realm of speculation. Disciplined, mathematically grounded speculation, but speculation nonetheless. Let us explore the cracks in the cosmos, the places where the standard model might be breaking down, and the exotic proposals that physicists have put forward to explain why two numbers refuse to agree. Part 5. Cracks in the Cosmos. The universe is patient with our ignorance. It does not hurry us toward answers. It simply presents its data, its starlight, its radiation, its gravitational whispers, and waits for us to make sense of it. And sometimes, the data tell us that the story we have been telling ourselves is incomplete. The Hubble tension is one of those moments. It is a crack in the elegant edifice of modern cosmology, a place where the equations that have served us so well for decades develop a quiet but persistent flaw. And the physicists trying to repair it have proposed a dizzying array of possibilities, each one requiring us to rethink some fundamental aspect of the universe. Let us consider the leading candidates one by one. The first, and perhaps most widely discussed proposal involves dark energy, the mysterious force that is driving the accelerated expansion of the universe. In the standard lambda-CDM model, dark energy is described by Einstein's cosmological constant, a fixed amount of energy inherent in empty space. This energy does not dilute as the universe expands. It does not change with time. It is simply there, a constant, unchanging presence that exerts a gentle but relentless outward pressure on the fabric of space-time, causing the expansion of the universe to accelerate. But what if dark energy is not constant? What if it changes over time? What if, in the early universe, there was an additional component of dark energy? A brief pulse of accelerated expansion that is not present today. This idea, known as early dark energy, proposes that for a short period after the Big Bang, a form of energy that behaves like dark energy temporarily boosted the expansion rate, subtly altering the dynamics of the early universe before decaying away. This extra push would change the size of the sound horizon, the characteristic scale imprinted in the CMB fluctuations, which in turn would change the inferred value of the Hubble constant from CMB observations, potentially bringing it into agreement with the local measurements. Early dark energy is an elegant idea, and it has been the subject of intense theoretical and observational scrutiny. Several models have been proposed, with names like the new early dark energy model, axion-based models, and chain early dark energy. Some of these models can reduce the Hubble tension significantly, but none of them eliminates it entirely without introducing other problems. The CMB fluctuations are extraordinarily sensitive to the physics of the early universe, and adding a new component of energy changes not just the Hubble constant, but also other observable quantities: the matter-power spectrum, the amplitude of fluctuations, the angular scale of the acoustic peaks. Fitting all of these simultaneously with an early dark energy model is challenging, and some analyses suggest that the cure may be as problematic as the disease. A second possibility involves dark matter, the invisible substance that makes up roughly 27% of the total energy content of the universe. In the standard model, dark matter is cold. It moves slowly compared to light, it interacts with ordinary matter only through gravity, and it is stable over the lifetime of the universe. But what if dark matter is not entirely stable? What if some fraction of it decays over time, converting its mass into radiation, into dark radiation, a hypothetical form of energy that does not interact with light or ordinary matter, but contributes to the total energy density of the universe? If dark matter decays, the energy density of the universe evolves differently than the standard model predicts. In the early universe, when more dark matter was present, the expansion rate would have been slightly faster. As dark matter decayed, the balance between matter and radiation would have shifted, altering the dynamics of the expansion in ways that could reconcile the CMB and local measurements. This is a fascinating idea because it would mean that the dark matter we observe today is not the same dark matter that existed in the early universe. It has been slowly, quietly transforming itself into something else, and the Hubble tension is the first observational hint of this transformation. A third possibility is more radical still. It involves modifying gravity itself. General relativity has been tested with extraordinary precision in a wide range of environments: in the solar system, around pulsars, during gravitational wave events. In every test, it has passed with flying colors. But all of these tests have been conducted on relatively small scales, the scale of stars, planets, black holes. On cosmological scales, the scale of the entire observable universe, gravity has not been tested with the same rigor. The lambda CDM model assumes that general relativity works perfectly at these scales, but this assumption is just that, an assumption. If gravity behaves differently on very large scales, if there are modifications to general relativity that become significant only when you zoom out to the level of the cosmic web, then the relationship between the early universe and the present day might be different from what the standard model predicts. One particularly intriguing modified gravity theory is known as MOND, or modified Newtonian dynamics. Originally proposed by the Israeli physicist Mordechai Milgram in 1983, a MOND was designed to explain the rotation curves of galaxies without invoking dark matter. The idea is that at very low accelerations, the kind experienced by stars in the outer regions of galaxies, Newton's law of gravity is slightly different from its familiar form, producing stronger gravitational effects than expected. MOND has had some notable successes in explaining galactic dynamics, but it struggles to account for observations on larger scales, such as the dynamics of galaxy clusters and the fluctuations in the CMB. The story of galaxy rotation curves is itself worth pausing over, because it illustrates how the universe has surprised us before. In the 1960s and 70s, the American astronomer Vera Rubin and her collaborator Kent Ford measured the rotation speeds of stars in spiral galaxies. According to Newton's law of gravity, stars in the outer regions of a galaxy, far from the dense central bulge, should orbit more slowly than stars closer to the center, just as the outer planets of our solar system orbit more slowly than the inner ones. But Rubin and Ford found that the rotation speeds remained roughly constant all the way out to the edges of the galaxies they observed. The stars were moving too fast. Either Newton's law of gravity was wrong at these scales, or there was a massive amount of unseen matter, dark matter, providing the additional gravitational pull needed to keep the stars in their orbits. The scientific community eventually settled on dark matter as the explanation, and the lambda CDM model was built around this assumption. But Milgram's alternative has never been fully ruled out, and the Hubble tension has given it new relevance. A group of researchers from the universities of Bonn and St. Andrews has recently proposed that MOND, when properly applied to the analysis of local distance measurements, could resolve the Hubble tension entirely. Their argument is that the peculiar velocities of galaxies, their motions relative to the smooth expansion of the universe, are different in a MOND-like universe than in a lambda CDM universe. In standard cosmology, the peculiar velocities are relatively modest, and their effects on the Hubble constant measurement can be accounted for with straightforward corrections. But in MOND, the peculiar velocities can be significantly larger. Bulk flows of matter on scales of hundreds of millions of light-years, driven by the modified gravitational dynamics. If these larger peculiar velocities are not properly accounted for in the analysis of supernova data, they could systematically bias the local measurement of the Hubble constant upward. In a MOND-based analysis, the bias disappears, and the tension evaporates. This is a controversial claim, and it has not been widely accepted. But it illustrates the range of possibilities that the Hubble tension has opened up. When the data refuse to fit the model, either the data are wrong or the model is wrong, and increasingly it is looking like the model might be wrong. there is another thread worth following here, one that involves dark energy itself behaving in unexpected ways. In the standard lambda CDM model, dark energy is described by a cosmological constant, and its equation of state parameter, the ratio of its pressure to its energy density, is exactly -1. This means dark energy exerts a constant, unchanging negative pressure on the universe, driving the accelerated expansion at a steady rate. But what if the equation of state is not exactly -1? What if dark energy evolves over time, growing stronger or weaker as the universe ages? This possibility, known as dynamical dark energy, has been explored theoretically for decades, and recent observations have given it a surprising boost. The Dark Energy Spectroscopic Instrument, DESI, a remarkable machine mounted on a telescope in Arizona that can measure the redshifts of 5,000 galaxies simultaneously using a forest of robotic fiber optic positioners, released its first-year results in 2024. Those results hinted, tentatively with caveats, that dark energy may not be constant after all. The data showed a slight preference for a model in which the equation of state of dark energy changes over time, evolving from a value more negative than -1 in the past to a value closer to -1 today. If this result holds up, and it is, still too early to be certain, it would be a seismic shift in our understanding of the cosmos. A varying dark energy would change the expansion history of the universe in ways that could affect the relationship between the CMB and the local measurements, potentially easing the Hubble tension. It would also raise profound new questions. What is dark energy made of? Why is it changing? And what does its evolution tell us about the fundamental forces and fields that govern the universe? The DESI results are just the beginning. The instrument will continue collecting data for years to come, and its final analysis, combining data from millions of galaxies and spanning billions of years of cosmic history, will provide the most detailed map of the universe's expansion history ever assembled. The Vera C. Rubin Observatory, currently nearing completion in Chile, will complement DESI by surveying billions of galaxies with its enormous camera, tracking the subtle distortions caused by gravitational lensing and the growth of cosmic structure over time. The European Space Agency's Euclid satellite, launched in 2023, is already mapping the distribution of dark matter across a third of the sky. Together, these instruments will subject the lambda CDM model to its most stringent tests yet. A fourth approach to the problem comes from an entirely unexpected direction: gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, ripples in the fabric of space-time caused by the collision of two black holes more than 1 billion light-years away. This discovery, which earned the 2017 Nobel Prize in Physics, opened a completely new window onto the universe. For the first time, astronomers could study the cosmos not with light, but with gravity itself. Gravitational waves carry information about the distances to the events that produce them. When two neutron stars spiral together and merge, for example, the amplitude of the gravitational wave signal depends on the distance to the source. By measuring this amplitude and comparing it to the redshift of the host galaxy, which tells you how fast the galaxy is receding, you can calculate the Hubble constant. This technique is completely independent of both the cosmic distance ladder and the CMB. It does not rely on Cepheids, or supernovae, or the physics of the early universe. It relies on the pure geometry of space-time as encoded in the gravitational wave signal. The first gravitational wave measurement of the Hubble constant came in 2017 from the neutron star merger event GW 170817. The result was roughly 70 kilometers per second per megaparsec, with large uncertainties. It was consistent with both the local and the CMB values, which was tantalizing but not yet decisive. As more events are detected, the uncertainties will shrink, and gravitational waves may eventually provide the independent tiebreaker that cosmology so desperately needs. But the most creative gravitational wave approach came in early 2026 from a team of physicists at the University of Illinois and the University of Chicago. Rather than relying on individual gravitational wave events, they proposed using the stochastic gravitational wave background. The faint, cumulative hum produced by countless distant black hole mergers, too numerous and too faint to be detected individually, but collectively producing a subtle background noise in the gravitational wave detectors. By analyzing whether this background hum is present or absent in current data, the researchers can constrain the Hubble constant from an entirely new angle. Their technique, which they call the stochastic siren method, represents a completely novel way of probing the expansion rate of the universe, one that uses entirely different physics from any previous approach. When they applied this method to existing gravitational wave observations from the LIGO-Virgo-Cagra collaboration, they found that the absence of a detectable background signal rules out some of the slower expansion scenarios, a result that, when combined with previous individual event measurements, slightly favors the higher local value of the Hubble constant. The measurement is not yet precise enough to resolve the tension on its own, but it is a proof of concept, a demonstration that there are ways of measuring the expansion rate of the universe that we had not even imagined a few years ago. And then there is gravitational lensing. When light from a distant quasar passes near a massive galaxy on its way to our telescopes, the galaxy's gravity bends the light, acting as a cosmic lens. If the geometry is right, the lensing can produce multiple images of the same quasar, 2, 3, or even 4 images, each corresponding to a different path that the light has taken around the lensing galaxy. Because these paths have different lengths, the light from each image arrives at slightly different times. If the quasar varies in brightness, which many quasars do, the variations will appear in each image, but with a time delay that depends on the path length difference, which in turn depends on the distances involved and, therefore, on the Hubble constant. The TDCOSMO collaboration has been measuring these time delays with increasing precision, using a technique called time delay cosmography. Their most recent results, combining observations of multiple lensed quasar systems, yield a Hubble constant of approximately 71.6 kilometers per second per megaparsec, closer to the local value than to the CMB value, and completely independent of both the distance ladder and the CMB. This result is consistent with the idea that the higher value is correct, though the uncertainties are still too large to be definitive. What is remarkable about this measurement is its independence. It does not rely on any of the same assumptions as the Cepheid supernova distance ladder. It does not depend on the physics of the early universe. It uses entirely different objects, entirely different physics, and entirely different data, and yet it arrives at a similar answer. This kind of independent confirmation is the gold standard in science. When multiple independent methods, each with their own strengths and weaknesses, each susceptible to different systematic errors, all point in the same direction, the case becomes compelling. The universe, it seems, is expanding faster than the standard model predicts, and no one knows why. There are other proposals on the table. Some researchers have suggested that the universe might not be as homogeneous as we assume, that we might live in a region of space that happens to have a lower than average matter density, a local underdensity or void that would affect the local expansion rate without being reflected in the CMB. This idea, sometimes called the local void hypothesis, is based on a simple physical intuition. If the matter density around us is lower than the cosmic average, then the gravitational pull retarding the expansion is also weaker, and the local expansion rate would be higher than the global average. This would make the nearby universe appear to expand faster than the CMB predicts, creating an apparent tension that is really just a local anomaly. The idea is appealing in its simplicity, and there is some observational evidence that we do, in fact, live in a region of modestly below average density, a local underdensity that extends out to several hundred million light-years. But the calculations show that the void would need to be implausibly large and deep to account for the full magnitude of the Hubble tension. A void large enough to produce a 6-unit discrepancy in the Hubble constant would stretch across a significant fraction of the observable universe, and its existence would produce other observable signatures: anisotropies in the CMB, bulk flows of galaxies, variations in the supernova distance-redshift relation that have not been convincingly detected. Most cosmologists regard the local void as an insufficient explanation, though it may contribute a small fraction of the discrepancy. Others have proposed that the neutrino sector of particle physics might hold the key, that neutrinos, those ghostly particles that barely interact with anything, might have properties slightly different from what the standard model assumes, altering the expansion dynamics in subtle ways. In the standard model of particle physics, there are 3 types, or flavors, of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Each has a tiny but non-zero mass, a fact established by neutrino oscillation experiments, which showed that neutrinos can change from one flavor to another as they travel, a phenomenon that is only possible if they have mass. But the standard model of cosmology assumes that there are exactly 3 neutrino species, each with a specific contribution to the radiation density of the early universe. What if there is a 4th neutrino, a sterile neutrino, so called because it does not interact through any of the known forces except gravity? A sterile neutrino would contribute to the radiation density of the early universe, changing the expansion rate during the epoch when the CMB was formed. This would alter the relationship between the sound horizon and the Hubble constant, potentially bringing the CMB and local measurements into closer agreement. The idea of sterile neutrinos has a long history in particle physics, motivated by anomalies in neutrino oscillation experiments and by the need for a dark matter candidate. But the evidence for their existence remains inconclusive, and the cosmological constraints on their properties are tight. Adding a sterile neutrino to the cosmological model can reduce the Hubble tension, but it also changes other observable quantities: the abundance of light elements produced in Big Bang nucleosynthesis, the damping tail of the CMB power spectrum, the growth rate of cosmic structure, and these changes are tightly constrained by existing data. The sterile neutrino solution, like many others, is a partial fix at best. Still others have suggested more exotic possibilities: extra dimensions of space, interactions between dark matter and dark energy, quantum gravitational effects, or even the breakdown of the cosmological principle itself. the assumption that the universe is the same everywhere. Some theorists have explored the idea that the universe might have a slight anisotropy, a preferred direction, that would affect the expansion rate differently in different parts of the sky. Others have considered the possibility that the physics of the very early universe, the epoch of cosmic inflation, the fraction of a second after the Big Bang when the universe expanded exponentially, might have left subtle imprints that are not captured by the standard model, but that influence the CMB in ways that bias the inferred Hubble constant. Each of these ideas represents a different way of modifying the standard cosmological model to accommodate the Hubble tension. And each one, in its own way, is telling us the same thing. The universe is more complex than we thought. The equations that have served us so well for decades, equations that correctly predict the abundance of hydrogen and helium, the large-scale distribution of galaxies, the temperature and fluctuations of the CMB, the ages of the oldest stars, may not be the whole story. There may be additional terms, additional fields, additional forces, additional particles, additional dimensions, that we have not yet discovered, but that leave their fingerprints in the precise value of a single number. H0. The history of physics is filled with moments like this. Moments when a small, persistent discrepancy between theory and observation turned out to be the key that unlocked a deeper understanding of reality. The anomalous orbit of Uranus led to the discovery of Neptune. The anomalous spectrum of hydrogen led to the development of quantum mechanics. The anomalous rotation curves of galaxies led to the hypothesis of dark matter. In each case, the discrepancy was small, the explanation was not immediately obvious, and the resolution transformed our understanding of the natural world. None of these proposals has emerged as a clear winner. Each one has its strengths and its weaknesses. Each one can explain some aspects of the data, but struggles with others. The Hubble tension remains an open problem, perhaps the most important open problem in cosmology today, and its resolution, when it comes, may reshape our understanding of the universe in ways we cannot yet anticipate, and perhaps that is the most exciting thing about it. Not the tension itself, but what it represents, the boundary of human knowledge, the place where our best theories meet the data and come up short, the frontier where new physics lurks, waiting to be discovered. In the history of science, some of the greatest advances have begun with exactly this kind of discrepancy, a small, persistent disagreement between observation and theory that, when finally explained, revealed an entirely new layer of reality. The anomalous precession of Mercury's orbit, a tiny discrepancy between the observed motion of the planet and the prediction of Newtonian gravity, led Einstein to develop general relativity. The ultraviolet catastrophe, a failure of classical physics to predict the spectrum of thermal radiation, led Max Planck to propose the quantization of energy, launching the quantum revolution. The unexpected uniformity of the CMB, which demanded an explanation for why the universe looks the same in every direction, led Alan Guth to propose cosmic inflation. Could the Hubble tension be the next such discrepancy? Could those 6 kilometers per second per megaparsec, the gap between 73 and 67, be the crack through which entirely new physics will emerge? We do not know, not yet. But the search is underway, and the tools are more powerful than ever. Space telescopes, gravitational wave detectors, CMB experiments, supercomputer simulations, and the collective intellect of thousands of physicists around the world are all converging on this problem. And when the answer comes, when someone finally explains why the universe is expanding faster than it should be, it will be one of the great intellectual achievements of our species. For now, though, we sit with the uncertainty. We hold the two numbers in our minds, 73 and 67, and we marvel at the fact that such a small difference can contain such enormous implications. Let us rest with that thought for a while. Let the numbers settle. Let the complexity of the cosmos wash over you like a tide, not a threat, but a lullaby. The universe is strange. The universe is vast. The universe, it seems, does not always cooperate with our attempts to understand it. But that is what makes it beautiful. Let us drift further, past the galaxies, past the cosmic web, past the microwave glow of the early universe. Let us travel to the very edge of what we know, and sit quietly in the presence of what we do not. The universe is expanding. The rate of that expansion carries a secret, and the secret one day will be told. But not tonight. Tonight, we rest. There is something deeply humbling about the Hubble tension, not just the scientific puzzle itself, though that is formidable, but what it reveals about the nature of human understanding. We have spent centuries building a picture of the universe. Layer by careful layer, observation by painstaking observation, we have constructed a model of reality that is breathtaking in its scope and precision. We can describe the first fraction of a second after the Big Bang. We can predict the abundance of hydrogen and helium forged in the cosmic furnace. We can trace the growth of structure from quantum fluctuations to galaxies. We can measure the age of the universe to within a fraction of a percent. And yet, two numbers disagree, and that disagreement tells us that our picture, for all its beauty and precision, is not complete. This is not a failure of science. It is science at its finest. It is the moment when the data push back against the theory, when nature refuses to be tidally captured by our equations, when the universe insists on being more interesting than we had anticipated. Every great advance in physics has been preceded by exactly this kind of creative friction. The uncomfortable recognition that our best model does not quite fit the observations, followed by the long, difficult, exhilarating search for a better one. The astronomer, Vera Rubin, whose observations of galaxy rotation curves provided some of the strongest evidence for dark matter, once said that in a spiral galaxy, the weights of all the stars together account for only a fraction of the mass needed to hold the galaxy together. The rest is invisible, unknown, and yet it is there. The universe, it seems, is made mostly of things we cannot see. The Hubble tension may be pointing us toward yet another invisible truth, another layer of reality that we have not yet learned to perceive. Perhaps it is a new form of energy. Perhaps it is a new behavior of gravity. Perhaps it is something so strange that we do not yet have the language to describe it. Whatever it is, the tension tells us that it exists. The numbers do not lie. They simply wait for us to understand them, and understanding will come. It always does. Not quickly, not easily, not without wrong turns and false starts in the slow, grinding work of testing hypothesis after hypothesis against the unforgiving standard of observational data. But eventually, someone will propose a model that explains both numbers, that unifies the local and early universe measurements into a single coherent picture. And when that happens, the Hubble tension will take its place alongside the precession of Mercury and the ultraviolet catastrophe as one of the great anomalies that led to a revolution in our understanding of the cosmos. Until then, the tension remains. A quiet crack in the foundation of cosmology, a whisper that something profound is waiting to be discovered. And in the silence of that waiting, there is a kind of peace. The universe does not demand that we solve its puzzles tonight. It simply asks that we pay attention, that we keep looking, that we remain, in the deepest sense, curious. And so we drift, through the dark spaces between the galaxies, through the microwave glow of ancient light, through the invisible web of dark matter and the mysterious push of dark energy, through the fabric of space-time itself, stretching and expanding with every passing moment, carrying us all, every atom, every star, every galaxy, on a journey without a destination, guided by numbers we do not yet fully understand. The universe is expanding. It has been expanding since the first instant of time. And the rate of that expansion, the speed at which space itself is stretching, contains a secret that may unlock the next great chapter of human knowledge. 73 or 67. The answer, when it comes, will change everything. But for now, it is enough to know that the question exists. It is enough to lie here in the quiet dark and feel the immensity of what we do not know pressing gently against the boundaries of what we do. The stars are still burning. The galaxies are still receding. The cosmic microwave background is still whispering its ancient code. And somewhere in the gap between two numbers, a gap of just 6 kilometers per second per megaparsec, the next revolution in physics is waiting to be born. Think about what it means that we can even ask this question. A species that has existed for a mere few 100,000 years, a blink of an eye in cosmic time, has managed to measure the rate at which the universe is expanding with a precision of 1%. We have built telescopes that collect the light of stars that died before our solar system existed. We have constructed detectors that can feel the tremor of space-time caused by black holes colliding a billion light-years away. We have launched satellites that map the afterglow of the Big Bang with an accuracy that would have seemed like fantasy to the astronomers of just a few generations ago. And yet, the universe remains one step ahead of us. Every answer we find leads to a deeper question. Every measurement we make reveals a new mystery. The Hubble tension is not a failure of human ingenuity. It is a testament to it, a sign that we have pushed our understanding so far with such precision that we have bumped up against the boundaries of what our current theories can explain. There is a certain beauty in not knowing, in sitting with the question rather than rushing to the answer, in allowing the mystery to exist, whole and undiminished, without needing to reduce it to a formula or a number. The universe is under no obligation to be simple. It is under no obligation to fit neatly into our equations. It simply is, vast, ancient, expanding, and full of secrets. And we are here, tiny beings on a small planet, orbiting a modest star in the outer suburbs of an ordinary galaxy, in a universe that is 95% invisible. We should not be able to understand any of this. And yet, somehow, we do, at least in part. We have deciphered the language of light. We have read the story of the cosmos in the fluctuations of a microwave glow that has been traveling for 13.8 billion years. We have counted the heartbeats of pulsating stars in distant galaxies and used them to measure the geometry of space itself. That we can do this at all is miraculous. That we have found a discrepancy, a crack in our understanding, is not a cause for despair. It is a cause for wonder. It means the story is not over. It means there is more to learn. It means the universe still has something to teach us if we are patient enough to listen. Close your eyes. Let the numbers go. Let the tension dissolve into the vastness, like a single photon released into the infinite dark. the universe will keep its secrets for one more night. And you who have traveled with us across billions of light years, through billions of years, past the boundaries of the known and into the shadow of the unknown, you have earned your rest. Breathe slowly. Feel the weight of the day dissolve into the vastness of space. Let the gentle rhythm of your own heartbeat remind you that you are here, on this small, warm planet, orbiting an ordinary star, in the outer arm of an ordinary galaxy, in a universe that is far stranger and far more beautiful than anyone ever imagined. Where are you listening from tonight? Wherever you are, beneath the stars or beneath a roof, in silence or in the quiet company of someone you love, know that the same light that carries the secrets of the cosmos is falling gently on your skin. The same atoms that were forged in the hearts of ancient stars are beating in your chest. You are not separate from the universe. You are the universe, contemplating itself, asking questions, seeking answers, and sometimes, on the best nights, learning to be at peace with not knowing, wishing you a peaceful night beneath the stars,